I just made a change in Pascal source code here and saved it on a 40-year-old computer, Apple Lisa here. It doesn't feel like it's 40-year-old. I have it on my t-shirt with the history of computers. I think it's somewhere here. But it feels very modern in the way that I have a window open, actually multiple windows open. I can copy and paste. I can use graphical UI in a very intuitive way. So yeah, it feels pretty modern, even though it's a bit clunky for today's standards. But never mind that. The reason that I want to include Apple Lisa in our series of Understanding Computer Sound is that it possesses two very specific features that make it unique in how sound was produced. Even though it is just a 1-bit output sound computer, just as ZX Spectrum or Apple II that we talked about earlier, it makes it, those two features, which I will talk about, make it a bit unique in the spectrum of computers of the late 70s and early 80s. It makes it closer, it makes it resemble maybe the implementation of PC the speaker in early PCs. But it's not the same. It's not the same. So I think it's worth to devote a short episode of Understanding Computer Sound to our Apple Lisa. Let's start by running two simple programs written in Pascal. Pascal is a built-in language into the workshop suite, which was available for Lisa developers. It's one of the languages, and lots of Lisa software was written in Pascal. But I wrote two simple sound-producing programs. One of them shows the scale of sounds or pitches available to Lisa programmers, and let's run it now. So it was just sliding across multiple pitches in a very fast way, producing this sort of gliding or zapping effect. But you must have noticed something else, something that we could not really experience in ZX Spectrum or Apple II. There was volume control. We started soft and we ended loud. Let's try again. Eight levels of volume controlled from software. That's a very new thing in our series of Understanding Computer Sound. We were unable to control volume in any reasonable or prescribed way in ZX Spectrum Apple IIs. We only did workarounds, remember, by, for example, modulating the pulse width. But here, the programmer has a function available, or API available in ROM to control volume. How it's implemented, we'll talk about that later. Interesting way in how it's implemented. For now, you've heard the effect of it. And I must tell you, it's not an accident that I keep a separate recorder here, because normally I record all audio from this Lisa similarly to other computers we talked about. I recorded by tapping into the audio path signal, audio signal path somewhere on the main board of the computer. So I tapped similarly here. You can see it from that camera view, but I'll add a picture later. The signal is tapped and run into this USB interface, then to a computer and recorded. But I also, this time I added a separate recorder here, and is it recording? Let me see. It's not. So let's record it once again, just to show how loud the loudest volume is. The speaker in Apple Lisa is really powerful. It is situated below the CRT, below the tube here. I think it's 0.5 watts or 0.75. Never mind that. It's large and it's powerful. Let's run the program again. This time the recording that you've heard was from this recording here, not from the signal path that I tapped into. Also, the timbre and the general feeling of the sound is different, as you see, because I'm tapping in the middle of the amplifier section, whereas this recorder is recording the Lisa as it sounds from the speaker. So slightly different. Now, so that was about volume. Let's have a look at another Pascal program and let's see what it can do. And I wonder if you notice what's so special about it compared to Apple II and ZX Spectrum. It's running already. It's just sound, nothing special. But the sound is playing. It's being recorded. It's continuous. But at the same time, the Pascal program is doing something. So the special thing about it is, of course, the concurrency. The sound can play while the computer is doing something else. We have not seen that before. We only saw tricks how that can be worked around, or how it can be achieved using certain very clever programming, but it was never available by default to the programmer. Let's run the program again. The sound starts playing. There's an instruction in Pascal which says noise, and you just give it pitch, you don't give it duration, and you just let it run. Then the program can do something else. I just put a counter here which displays subsequent integer numbers, and it just loops. And then at the end, when it finishes, there's another instruction related to sound, which is simply called silence. Switch the signal off. How those two features, volume control and being able to do something while the sound is playing, how that was achieved? Well, we'll talk about that now. The first mechanism, the first design decision that I want on the part of Apple Lisa designers that I want to talk about is shift register. Shift register is a generic method for transforming parallel data to serial and vice versa. It can be used for serial communication, to drive LED displays, and for many other applications. The shift register which Apple Lisa uses for sound generation is implemented in MOS 6522 Versatile Interface Adapter, or VIA chip. Lisa has two of these chips, one mainly responsible for disk operations and the other one mainly responsible for keyboard and mouse input-output. The latter is also used for sound. Sound is generated by first pre-programming the 6522 to enable continuous shift-out. Continuous or rotational shift-out works by taking bits 0 to 7 from the parallel data bus and outputting them in a serial manner on CB2 pin continuously. That is, the most recently output bit goes back to the end of the queue. The frequency of output is governed by clock T2. So the programmer has to set the T2 clock corresponding to node frequency, the number of rotation cycles corresponding to node duration, and the pattern of 8 bits corresponding to shape of pulse train. The moment the 8 bits are uploaded to the VIA chip, rotation starts and the CPU is free to do something else. That was the theory of shift register. I wanted to try it in practice. I wanted to reproduce the same way that Lisa controls its 6522, which then controls the sound wave. I wanted to reproduce that using Arduino and an actual 6522, original MOS 6522 chip. I connected it all together and I succeeded in making it running. I'm sharing my code for the Arduino code for that in my article, but do not learn from that code. This is terrible programming. I have no experience at all in programming microcontrollers or microprocessors. So it's like a POC. It works, but it's definitely not the way it should be written. So what I'm doing is I'm setting the 6522 VIA in shift out operation mode, shift out controlled by the T2 timer. Then I'm setting the T2 timer to certain value, which corresponds to the frequency set by Lisa. I'm then setting the shape of the sound of the pulse train by defining certain pattern of bits, and I'm uploading those bits to 6522 shift register. Once we upload it there, it immediately starts shifting out through the CB2 pin to which I connected oscilloscope probe. So once I started running, the code will run once and momentarily, while the chip will keep producing a certain pulse train pattern. So let's see if that works. It worked. You see the pattern here. When I zoom it in, it corresponds exactly to the pattern of ones and zeros, which we uploaded to the shift register using the data lines, the parallel data lines, 8 lines. So the high states represent ones, so this is single 1, 0, 1, 0, 2 ones, 2 zeros, 1, 0, again and again and again. And the pattern keeps being shifted out. At that time, the CPU is free to do something else, while 6522 is continuing to produce sound. This is what we saw in our Pascal program earlier, when I started the sound, then made the program do something else in a loop, and only then, at my discretion, I ended sound producing. So this is how shift register works. Again, it was a very interesting experience to build this thing together. I'll share the connections and that terrible code in my article. Another solution, the one that is responsible for controlling volume, has been implemented in Apple Lisa using what is called Resistor ladder. Very interesting concept, known to every person who is passionate about electronics. For myself, it was a new concept, but extremely ingenious. It's basically a way to convert digital signal to analog, a very simple way and very elegant way. But in Apple Lisa, it was not really to convert the analog the digital representation of sound into analog sound, it was only used to convert the digital representation of volume level to the actual voltage level in the amplifier section. Let's look at the resistor ladder. Resistor ladder is a circuit in which data lines are connected to resistors arranged in such a way that changing the high-low states of the data lines affects the voltage in the circuit. The digital bits, from the least significant to the most significant, are weighted in their contribution to the output voltage. In fact, a resistor ladder is a simple digital to analog converter which, given enough number of bits and precise resistor values, can serve as a sound DAC. However, in case of the Lisa, instead of modulating the shape of the sound wave, it modulates its overall amplitude. That is, it serves as a digital volume controller. The 3-bit resistor ladder used in the Lisa gives a programmer 8 different output voltages to select. That is 8 different volume levels. Similarly to shift register, I wanted to experiment with resistor ladder in practice, so I built a simple resistor ladder out of the resistors that I had at home and connected it to 3 digital lines. Similarly as it's done in Lisa, 3 digital lines coming from the via go to the resistor ladder to control the volume, and the programmer has the control over those 3 digital lines. So 3 digital lines are connected to this cobweb of what looks like cobweb of resistors, but they are actually arranged in a ladder pattern. I'm gonna share the schematics for that in my article linked below. But let's see how that works. So basically, I upload the code, I run the code in Arduino and connect the other probe to the end of the ladder, and there it is, beautiful. So what we see here is 8 levels of volume nicely represented. The code in the Arduino basically goes through all possible states of the 3 bits, which is the total of 8 bits, from 0 to 111, and it repeats the pattern every several milliseconds, I think. So it goes from 0 here, like building a nice staircase in our oscilloscope view, all the way to 111, after which it drops again to 0. We see even from here that we can build a nice wave. This is basically a very rough triangle wave out of 3 bits. So we're dealing here, as I said, with a digital to analog converter implemented in a very simple, elegant way. And it can be used to build waves of arbitrary shape, given enough resolution, enough digital lines, and enough sampling frequency. So very nice idea, I love it. Again, in Apple Lisa, it has been used to control volume. Let's try again, run the Pascal program which I showed in the beginning, and see how that volume goes from 0 to 7. Again, 7 is very loud. It was very loud, and I can see one of the neighbors looking through my window what's going on here. No, I'm not playing games, I'm experimenting with vintage sound. That was the resistor ladder. Understanding hardware side is one thing, but I also had a lot of fun programming Lisa in low-level assembly language. And it was a humbling experience, not only because I learned how much I don't know, but also because I met quite a few extremely helpful, kind people on the way, who are much more knowledgeable than I am, and without whom I would have never been able to experiment with sound the way I did. So first of them is Ray Arachilian, the author of Lisa Emulator. I started by building programming framework within Lisa Emulator, and the first experiments, countless experiments, to even figure out how programming works for Lisa. I wrote that using cross compiler and tested on Lisa Emulator. Without it, the experience would have been at least much more frustrating, but most likely I would have never been able to even write anything properly for the Lisa. So amazing Lisa Emulator, amazing piece of software. I wasn't able to test the sound routines themselves properly because of a bug in Lisa Emulator on which Ray Arachilian is working to be fixed. But anyway, that Lisa Emulator was very helpful. Another person that helped me a lot was Tom Stapleton, who not only wrote amazing Mandelbrot demo for the Apple Lisa, but also many very helpful input-output routines, which I read very closely to understand how they work before I started experimenting with sound, and who also wrote very helpful conversion routines, which enable, written in Python, which enable producing disk images, which I then upload to the physical Lisa in a very easy manner. I'll share the code for that later. So both Tom and Ray, very active on the Lisa List forum, were very helpful in the first steps there, and my big thanks go to them. How we can we generate sound from within assembly language in Lisa? Let's have a look at that. It's not that sophisticated. In the code that I will talk about in a minute, I used the built-in ROM routines for generating sound in Lisa. I adapted it to be a bit more flexible, specifically to be able to control the pulse train pattern shape. Let's quickly dive into the very simple code that I wrote, so that we know how sound is generated on a low level. Before we look into the more exciting low-level ways to generate sound on the Lisa, let's take a step back and look again at the Pascal code we discussed before. The very big change compared to BASIC's implementation of beep, for example ZX Spectrum, is the fact that the processor is released to do its next task right after calling beep. And as a result, in Apple Lisa's Pascal, the call to beep is not blocking. This means that a call to beep right after an earlier one causes overriding the earlier one immediately, regardless of the duration specified in the earlier one. I wanted to code the notes of a Polish nursery tune about a little goat, but to play notes with expected timings, I had to introduce additional artificial delays between beeps. And because Lisa's Pascal doesn't have a built-in sleep or wait function, I had to write my own delay procedure, which was an educating experience in itself. The experience was fun because each time I made a mistake, I had to recompile the code, relink it, and rerun it, which on a 40-year-old computer is a lesson in patience and persistence. The finished tune sounds like this, and I'm sharing its source code and compilation steps in the article linked below. Even more fun was low-level coding in assembly language.
If one wants to go that path, they are responsible for coding the communication with the 6522 VIA chip. That is, for setting the correct value to the auxiliary control register in order to enable shift-out operation, setting the free-running shift-out mode controlled by timer 2, setting the actual timer value, and finally sending a pattern to the shift register. I started out by copying Lisa's built-in ROM implementation of tone procedures. This helped a lot because all the constants required for addressing the VIA chip were already set for me, and I did not have to calculate them based on the hardware manual. And the actual steps to load VIA's shift register, the same which I had to write manually in my Arduino exercise mentioned earlier, were already there to use. The only modification I made was to replace the hard-coded 50% duty cycle square wave with a variable, which I could set in my score. The rest was fun. I used the frequency tuning app to arrive at pitches for individual notes, and also defined constants for note durations. The last part was to write the actual music subroutines and arrange them into a complete piece. For each note I was able to specify the volume and pulse train, and I used that capability a lot, as well as effects which we discussed in other episodes like fast arpeggios. To hear the end result, you need to wait until later into the video.
So that's the assembly code controlling sound generation in Apple Lisa. It's all great, but I feel that much more can be done. And before I show the two very simple tunes that I wrote in assembly language myself, let me say that I feel that there's a lot more to explore, a lot more that can be achieved, especially because we can get away from the pattern of shifting out continuously. We can engage the CPU a little bit more and control the shift register content with every iteration, because we have clear signal back from the 6522 when the shift has ended, shift out has ended. There's a signal set on IRQ, one of the IRQ pins, which we can use to know that it has been shifted out, so we can upload something new to the shift register. This way we will control much more than repetitive pulse train pattern. We can control, we can build much more elaborate wave shapes. Especially we can experiment much more with pulse width modulation and achieve polyphony this way, achieve much lower sounds than Apple Lisa is by default able to produce because of this shift register limitation. So there's a lot that can be explored, and I'm not the first that started exploring shift register sound generation, of course. Actually, the very first person I think who ever attempted that and achieved a lot of success was Hal Chamberlain, author of this amazing book, Musical Applications of Microprocessor. It's a Bible of computer sound generation, something that I love reading, and I recommend highly to anyone who is interested in the subject. But Hal Chamberlain was the first one to use, I think, that's how much I managed to learn, was the first one to try and use 6522 shift register to output sound, and he did that in Commodore PET home computer, which by default the early versions didn't have sound generation capabilities. So he used 6522 to generate sound in a very similar way as Lisa did. I can speculate that Lisa designers saw his work on that subject in Commodore, because Commodore PET was earlier than Apple Lisa, and I can speculate that they adopted the idea from him, but I'm not sure about it. Another person who much later dug into what can be done with 6522 VIA was Shiro, whom we know from ZX Spectrum demo scene work, an extremely prolific developer and musician for the ZX Spectrum and other retro computer demo scene. He was also working with Commodore PET with the shift register of the 6522 VIA, and he achieved some amazing results there. I'm linking to his work and his article on that in my article. So have a look at that. From what I know, he also explored the idea of shifting out once, getting the interrupt, and uploading a different pattern to the shift register, so that much more elaborate sound effects can be done. But he wasn't working specifically on Apple Lisa, so I feel that a lot more can be done on Apple Lisa. I feel that unfortunately I don't have the skills for that, but I would love someone, maybe Shiro or someone else, people who are much more knowledgeable in machine language and assembly coding, to write a tracker for Apple Lisa, or at least an engine that can be used to produce much more elaborate music using the VIA 6522, and also using the very unique feature of volume control, which I demonstrated earlier. But having said all that, I feel it's time for a small demo, something that I wrote in assembly language myself. So let's listen to two simple pieces of music which basically use all the techniques that we learned, simple beep techniques put together, and also using some specific features for Apple Lisa. So we will use arpeggios, we will use volume control. You will see volume control for producing some echo effect. We'll see also wave shape or pulse shape modulation, which will result in modulating the timbre of sound. Let's play. And I also need to thank the creators of Floppy Emu solution for Apple Lisa, which allows easy uploading of disk images to Lisa without bothering with physical floppy disks. Let me upload the first piece of music using that Floppy Emu. Well, it was simple and short, but it used the arpeggio effect and also a little bit of volume modulation. Let's try the other one. As I said, the actual sound produced by Apple Lisa speaker is a bit different. Let's record it from the speaker and let's see how that sounds. So again, this showed volume modulation, pulse width modulation, and arpeggio effects all in one tune. I hope you liked it. As I said, Apple Lisa can do much more. It's a matter of now taking it to skilled hands of a programmer or a developer and letting them have fun with it. I hope someone picks up those ideas and builds a really good music, one-bit music engine for Apple Lisa. I'd love to see that. And as the last remark, and an interesting thing to mention, probably is the fact that Lisa initially was meant to have a slightly different sound subsystem. In pre-production models, the sound generated from within 6522 was not meant to go straight to the amplifier. Currently in production systems, it goes to a relatively simple amplifier circuit. It not only amplifies the sound, but also divides the frequency by 2. But in the pre-production models, apparently, and it can be read in pre-production documentation, which is available online. Apple Lisa was meant to have a CVSD chip, which would take the signal, the pulse train from 6522, and would do something more with it. It would create an arbitrary wave shape out of it, and only then output it to the amplifier. CVSD chips are used mostly for speech encoding and decoding, and Lisa was meant to have that capability as well, digitizing speech and playback of digitized speech. It even had input and output audio jacks in the original pre-production version, which was later dropped in the production version. But the CVSD chip also, as a side effect, was able to generate arbitrary sound waves. It would be interesting someday to check that out, how it worked in pre-production models, but I'm not sure if any exist that would allow us to experiment to that level. But in any case, Lisa designers apparently had a lot of fun designing the sound subsystem. They ultimately compromised on something that was probably relatively inexpensive, given the already very high price of Apple Lisa, and still quite advanced in the way, maybe not the way that game consoles are advanced in some were advanced in sound reproduction back then, but advanced in the way that it allowed sound generation without occupying the CPU too much. Lastly, it's worth mentioning, I mentioned that there was no demo scene for Apple Lisa. This is not entirely true. I found one demo made by Carnegie Mellon University students, I think, but I was unable to run it on my Apple Lisa 2. This is the more modern, newer version of Apple Lisa 2. To run that demo, you need an older version of Apple Lisa 2. The demo is called Requiem, and you can see it on YouTube. I'm giving a link to that YouTube demo and to the source code for that demo itself in my article. My Lisa hangs when it tries to play back that demo, but this is just a disclaimer that yes, there was some demos seen for Apple Lisa. From what I remember, that demo does not have any very advanced music. It's just beeps without much more than that. But it's still a demo, so we can't fully say that Apple Lisa didn't have a demo scene.